The index of refraction varies with thickness in very thin layers, as I've discussed in previous papers. The indices also vary with surrounding materials, and they'll vary with process and treatments. Procedures have been developed to cope with this in the design process. And in fact, the indices vary even in very thin layers within the layers in homogeneity. Here's some examples of silver, which are fairly dramatic. And in the very thin layers, we've got like 2 nanometers thick. Now, this is the crystal monitor thickness. And as the layers get thicker, this resonance seems to move until at some point the layer starts to coalesce from an island structure to a continuous structure. And we go through some transitions here at about 10 or 11 nanometers thick. And then as we approach 30 nanometers, we get a bulk property relationship. And the software that we develop interpolates between different measured thicknesses. If I had a thickness between 20 and 30 nanometers, for example, it would interpolate an intermediate index for this. Similarly, between 9 and 10 nanometers, we would interpolate at each wavelength. Here's the K values for silver in this case, where at about 30 nanometers, we settle into a more or less homogeneous case. But anything thinner than that, we have to accommodate variation in index. Here's a comparison of the difference between the interfaces. In this case, we've got silver on fused silica, and as a function of thickness and wavelength, for example, at 380 nanometers, we have this sort of thing as a function of thickness, and this is the N value. And all of these come to a convergence about at 30 here, which says this has become more like bulk values or coalesced or percolated, as some people say. Now, here's a different situation where the substrate has a 7 nanometer layer of aluminum oxide, then the silver layer of whatever thickness, and then a covering layer of 7 nanometers of aluminum oxide. And we see that this all converges and becomes percolated or coalesced at 20 nanometers instead of the 30 nanometers for this material combination. This is the K values, and again, about 30 nanometers for diffuse silica and air versus about 20 nanometers for the aluminum oxide on either side of the silver. Chromium behaves similarly. Very thin layers, the N value changes and eventually gets up to a bulk value. And the K value looks like this. So again, we'll interpolate in between these to get design with something, let's say that was 6 nanometers down in here. Here's some interpolated values for thin chrome layers for the N value and the K value. Now, if I want to make a black mirror with chromium, historically the assumption was made that the index values, including the chrome layers, are homogeneous for any thickness. We know this is not the case. And if we coat an opaque layer of chromium and then a metal dielectric stack on top of that, we can get a good black mirror design such as this. However, when we deposit it, we don't get those results. We basically get a result that looks like this. So we haven't achieved our goals. So this is typical of the common problem where coating produced does not agree with what was designed. And these are some of the problems that cause that. However, if I use the corrected index values in the design process, then I get a result that looks like this. And here are the thicknesses of the first design. And when I use those thicknesses and produce it with these thicknesses here, I get a no good result. But when I use the proper design processes, I'll get these thicknesses, which are notably different from those, but I get the good result of a nice black mirror. Now, inhomogeneity can happen even in these nano thickness layers. These are some models we might have. If the index versus thickness in a layer is continuous, we would get something like this sort of profile. If it is more dense, we'll say at the substrate, it'll grow like a cone or a pyramid. And if it gets thicker as a function, or it gets wider, we'll say as a function of thickness, it might grow like an ice cream cone. Or we could end up with spherical or elliptical or raindrop sort of configurations. So these are the various models. And if we want to model inhomogeneity, we might divide our layers into 2 pieces like this, or 3 pieces like this. Here is the spectral data taken, which are the dotted lines here. And if I try and fit that as a single homogeneous layer, this is the best fit I can get. So it's not totally satisfactory yet. If I divide it into 3 layers, upper, center, and lower, as compared to a single layer, I'll get these 3 index profiles for those. And similarly in the K values like this. If I use those triple layer fit, then I get essentially a very good fit here. A little bit something funny going on down here, but we'll not worry about that. And so here is the kind of approximation we'll deal with. In essence, let's say this this upper of 3 layers is thin or not very wide, medium wide and wide, etc. Here's a actual electron micrograph of silver in a dielectric matrix. And these now look essentially like spheres primarily of silver in the dielectric matrix, which probably has to do with post-processing, etc., so that the silver atoms probably migrate into a more spherical, lower energy configuration. So these are 5 very thin silver layers in dielectric. So here's the way I'm portraying it here. The thickness of the layer is from top to bottom. In this case, it's only 1 nanometer thick as measured by a quartz crystal monitor. And I'm plotting the indices of refraction horizontally here on a scale of 0 to 10 here. So this is the K value is approximately 6 and the N value is approximately 7. And even in this very thin layer, to get a good fit, I had to divide it into 3 pieces, and it's a higher N value at the top of that thin layer. Here's a comparison all on the same scale from the of that same sort of plot. So here's a very thin one, which is essentially the same as this one. And then as I get to 3 nanometers, it looks like this, and 6 nanometers and 12 nanometers. So this might look a little more like this in terms of assuming somewhat spherical shape. So in conclusion, the index properties of nanometer thick layers can now be derived from spectrophotometer scans of test depositions at various thicknesses. And then we've made the software to apply that and design with those layers and have much better confidence that the production results will agree with the designs. And this is even the case of a few nanometers thickness that have inhomogeneity. Thank you for your attention. Here's my contact information if you need to get a hold of me.